This tutorial is sort of an extension of the free fall 2D problem with wind drag. Again, we will be solving a second order differential equation using Euler's method by converting it into first order differential equations, but we have an additional term. So instead of falling in vacuum or moving in vacuum, we also have some drag force because of the medium. So, and if you remember from your fluid mechanics class, this drag force is proportional to the density of the fluid, but also the square of the velocity with which the fluid is moving through the medium, with which the object is moving through the medium. So in this case, if the wind velocity, which is v sub w, has some value, and the velocity of the object has some value, it's the relative wind direction and wind velocity that determine the drag force. So we find first what is the relative wind velocity vector, which is the wind velocity vector minus the velocity of the object, and then this is what we use to find out the drag force. It's half rho w squared, which is the velocity squared, times the drag coefficient times the area. And this is a unit vector that is just saying that this drag force is directed in the direction of the relative wind velocity. And as you can see, this is a dot product of the vector, so this will potentially give us the magnitude of the vector w squared. And we can find the unit vector by taking the w vector and dividing it by its magnitude. So this is simple vector geometry that you should know. And if we plug the value of w, which is vw minus v, then we get the second order differential equation as the force due to weight plus the force due to drag. Okay. And again, just like the last time, without the drag, we can convert it into 4 first order differential equations and create a state vector that and a slope vector. Convince yourself that this leads to this vector here, and our initial condition is the same as the last problem. So now let's look at its implementation. Again, the only difference compared to the previous implementation is where we find the velocity. So I have created these constants. So we have the wind velocity is minus 10 in the x direction and 0 in the vertical direction. So this is horizontal wind. And then we just treat rho as 1 for now, area as 0.01, and drag coefficient as 10. So I have calculated half rho CdA here, so we don't have to calculate it again and again. So let's implement this and see what we get. So we have half rho CdA and mg. And again, at the initial condition at t equal to 0, we know the position. Oh, in this case, the position has been changed to 40, so it's moving from a certain x direction locations just for the convenience of plotting. So let's go back here. Again, we create our time domain. In this case, we're going to run it for 10 seconds. And we have our state and time array for holding all the data. So in the loop, let's say for n is equal to 2, I will take you through this loop step by step. First, we find the relative velocity. So we know that the velocity of the object is in third and fourth elements of the state vectors, u and v. And to find w, we have the uw minus u and vw minus v. So we can do that in a single line by taking the vw, which is the wind velocity, minus the velocity vector, which is the third and fourth elements of the state vector. that gives us the relative wind velocity. And then we have the timestamp here. And here is the state update. And here we are saying that the current value of the state is the previous value of the state plus the slope times dt. And this slope is coming from here, half rho CdA, which is a single constant, plus square root of norm of W. So norm of W is W squared, and then we take the square root to get the magnitude of VW minus V. And the last term is W1, which is the UW minus U, as here shown. Okay. In a similar way, the fourth component is mg plus half rho CdA, the magnitude of the relative wind vector times the y directional velocity difference, so VW minus V. Okay. And the rest is pretty much the same code as from the last implementation without the drag. So when we run this, you can see how at 80 point, I'm showing the direction of the wind. It's blowing at 10 meters per second towards the western direction. So you can see as the object goes up with a velocity of 5 and 40, so 5 horizontal, 40 upwards, the wind drag starts to play its role. So let's run it without the wind drag. By that, we can just set this to 0, 0, and then again run it. You can see that the object will behave as there was no wind, or potentially there was no air. But if we put the wind drag there, then if we go back and put some wind drag, let's say we increase the wind drag to 15 meters per second and run this, the wind will start to play its role, and it'll move the object differently. So you can visualize how simple implementation of that second order differential equation gives you a very clear idea of the behavior of the object in the presence of gravity and drag.